Hello. So this is the final part of the circles chapter, and in this section, we're going to look at problems with triangles and circles. So triangles in a circle, and some circle theorems relating to triangles. Okay. So the first thing we're going to look at then is actually pretty very similar to what we looked at before with perpendicular bisectors, which is, again, as a remind, which we looked at previously. For any chord, say that one for example, any chord in a circle, and remember, chord is very simply just a line in the circle, right? A line between 2 points on the circle. Okay, then if we draw the perpendicular bisector, which again goes through the midpoint of the chord and is perpendicular to it there, okay, with the midpoint there, so it passes through the midpoint and is perpendicular. Every perpendicular bisector of any chord will always pass through the center of the circle. Okay, cool. um but I guess the problem is, what would be the center, right, in that case? Because we'd need the center to then work out, say, the equation of the circle. But we know it passes through the center, but we don't know exactly where that is. We just know it does. We can't find the point if we have one bisector line, okay? But we know it does. However, with that in mind then, what if we then consider two perpendicular bisectors? Let's copy that first one, that chord and the bisector there. The center has to be there somewhere, say. What if we then consider a third point on the circle, say there, and let's connect it to the other. Let's connect it to another point we already know. Let's say there. Let's draw a chord. Oh, here, right? Another chord, another line in the circle there. Then the bisector, the perpendicular bisector, would then look like that. Oh, hang on, a bit better. There we are. So then that'd be perpendicular there. And then what we've got then is a situation where both the perpendicular bisectors intersect at the centre. Well, that makes sense, because if every perpendicular bisector must pass through the centre, if we have two different bisectors, then they both must intersect at the centre. Okay. Well, then we got quite an interesting situation, in that if we have them 3 points on a circle, again, say here, here, and here, that is actually enough to find it. Oh, hang on. Let me draw a circle. That's not a circle. There we are. If we have any given 3 points on a circle, well, we can actually then determine where that centre is by finding two bisectors and intersecting and equating them together to find that centre point. And we can also then find the radius as well, which allows us to then find the equation of the circle. So actually, when we just have any 3 points on the circle, we can then find the equation of the circle. Okay. Again, that's all because of the fact that every perpendicular bisector passes through the center. So with that in mind, I'm going to note that every perpendicular bisector of any chord in a circle must pass through the center, and we saw that before, right? Okay, cool. So that means then that two different perpendicular bisectors both meet at the center. which then allows me to then, if I then can find the equation of the perpendicular bisector, which we did many examples of earlier in the chapter, we can do that if you know the points. We can then equate them together to find that centre, and we can then find the radius by considering the distance between the centre, which we then find, and a point on the edge, which will then be the radius. Okay, cool. Now, and we will look at examples in a minute with this in action. Don't you worry. But what this then means is because therefore any free given let me say that given any 3 points as a result, we can make two different perpendicular bisectors. And what that therefore means then is that we can find a circle. So any 3 points can form a circle, okay? Because once we find the two perpendicular bisectors, we can then find the centre and then the radius. That allows us to define and find a circle, right? The equation of the circle. So it's quite an interesting sort of idea there. That's take any 3 points whatsoever, any 3 points, we can then make a circle out of them. And so what we call that is and this is a particular type of circle, we call it. This would be called a circum. Oh, if we can spell it right. Circle, okay? Which is a circle defined through 3 different points, okay? Cool. We also call as well, if you want to be, we can also call the centre the circumcenter of that particular circle as well. Is called the circumcenter. Okay, but we don't use that very often. We don't really use the word circumcircle either. We just call it circle. But that's the notation and the keywords we use in case it comes up or whatever. But yeah, so we've got an interesting prospect, and we will see examples like this where we do find the equation of a circle. Given 3 points, we will see that in a minute. In one of the questions we look at. But that's the idea, right? 3 circles means we can find 2 different perpendicular bisectors, which both, as you can see in that example, as we just did, both perpendicular bisectors cross at the centre, because every bisector crosses at the centre. Therefore, we have the point of the centre to then find the equation of the circle. Okay, cool. So that's the first theorem. So that's really just a slight extension of what we looked at earlier with perpendicular bisectors. The second one is, and you should remember this from GCSE, and it's to do with another triangle. In particular, if we have then a generic circle, if we consider diameter, in this case, so that's the centre there. If you have any diameter, if then at the edges of the hang on, let me rearrange this a little bit. Let's instead do it that way. There we are. Okay, so let's draw the diameter that way. Now, if at the edges, both ends of the diameter, if they then both make chords, say there and there and there, and they both meet at the same point on the circle there, that angle that is formed there is actually is 90 degrees, right? And we call that the angle in a semicircle, okay? And you would have been familiar with that at GCSE as a circle theorem. So we call that angle in a semicircle is 90 degrees, okay? So we have a diameter, which obviously then splits the circle into 2 parts, so hence the word semi for semicircle, right? Then if we then go on to make another angle by then creating 2 further lines that meet together there, then that angle in the semicircle we made has to be right angle, okay? And again, we'll be looking at examples of that. Now you don't need to know the proofs of this, which I find quite interesting, because at GCSE you actually do need to know the proof of all the circle theorems. For A level, and I've checked the spec, you only need to be able to use them, okay? Which we'll be looking at questions using them obviously in a minute, but you don't need to know how to prove them. But I guess a very simple sort of way to know it is, well, actually we should know also that the angle at the center is twice the angle at the circumference. So again, if we have two radii, which again is here and here, so the diameter can be split into two radius or radii, then the angle actually is 180 degrees there, right? So it's angle on the line. Well, actually, then the angle at the center here, that'd be half of that of 90. Hence, it'd be a right angle. So very quickly we can see that. But yeah, but or a more direct way without a theorem, you could consider then splitting this into two different triangles by by creating another radii from the center to that point. Then you consider all the angles, okay, there, and there. Obviously, then you're going to have isosceles triangles because you got different radii which are all equal, and you can go from there. But I'm not going to go into the proof in that sort of detail here. All you need to know is that when we have an angle a triangle in a semicircle constructed in this way, it will be a right angle there, okay, and we will be using that there, okay. So those are the two other circle theorems we'll be referencing. Cool. So let's have a look at some examples. So this example then, we are given the points A, B and C, all drawn for us nicely on the diagram. First of all, it says, show that AB is a diameter to the circle. Well, I guess you might somehow think, well, let's just find the midpoint, because we know on the diameter the midpoint is the centre, but we don't know what the centre is, so it's not really going to tell us anything really. So we have to make use of a circle theorem, and actually this is a triangle in a semicircle, right? It's this is a diameter, and then they both make an angle there. But then, if we reference the angle, the theorem we just looked at, where the angle in a semicircle is 90 degrees, well, indeed, this angle is 90 degrees. There. So then that allows us to then prove that it's a diameter of a circle, right? Because we know the only way for that to be 90 degrees and for the theorem to apply is that this must be a diameter. So then the question then goes to, we need to prove that that angle is 90, okay, in order for that to be the diameter. So, well, how are we going to do that? Well, if it's 90, well, then it's a right angle triangle. What else do we know about right angle triangles? So I'm going to say if AB... Actually, no, I'm not going to leave it there for now. Well, we know right angle triangles is, well, trig and Pythagoras theorem. Now, we're proving that something is a right angle triangle. You're going to want to see that Pythagoras theorem applies, okay? How are we going to do that then? Well, Pythagoras theorem, again, if I sketch a right angle triangle, a generic one, and that's A, B and C, the hypotenuse, well, indeed, the two sides squared has to equal the hypotenuse squared. And that's what we're going to do. If that Pythagoras theorem applies to this right angle triangle, well, if it applies to the triangle, well, and the sides satisfy Pythagoras theorem, then it must be a right angle triangle, which means that must be 90. Anyway, so that's what we're going to do. We're going to then essentially prove or show that Pythagoras theorem applies to this triangle. How are we going to do that then? We need to know the sides. Well, we don't know the lengths of the sides, but we know the coordinates of all the vertices. That makes me think I can find the distance between them by the distance formula, which we used before as well. That's what we're going to do then. So we need the three sides. Therefore, well, we're going to find the three distances of the edges. Firstly, let's take AB here. So AB, That's going to be root, well, the change in x of the two coordinates a and b. So b is 4, take away -8, all squared, then the change in y squared. That'd be 5 at b, take away 1 at a, and there we are. Put that in the calculator. You will get 4 add 8 all squared. Add 5 take away 1 all squared. Gets you 4 root 10. Okay. Then we work out another side. Let's do AC, which will then be that side there. So then again, I'm going to do the same thing. Change in x then. Let's do it C. Well, it's -4 here for x. Then at a it's -8, so take away -8. All squared and changing y squared. Well, c is 9. Take away the y at a would be 1. And there we are. If we work that out, we would get -4 add 8 all squared. We get 4 root 5. Okay. And then lastly, the last side, BC. Which again is going to be then that side there. If we work that out, well then again we do change in x all squared. So let's do b first. For 4 for b, take away -4 for c all squared. Add 5 for b there for changing y. Then take away 9 all squared. Gets me it gets me 4 root 5, which is great because now I've got two sides the same. And you can see it kind of looks like it's double this, right? The AB looks like it's almost double. Okay, so those are the sides we've got. But then we need to check Pythagoras theorem applies. Well, then we need to consider the squares of all these, right? So AC squared, well, that's going to equal BC squared, right? Because they're the same. And so that's 4 root 5 all squared. Put that in a calculator, you would get 80, okay? Okay, well then we need to consider the other side squared, which is AB up here. Well, AB squared is going to be 4 root 10 all squared. So that's going to get me 160. Okay. Therefore, then we can then say that AC squared plus BC squared equals AB squared. Because 80 plus 80 is indeed 160. Cool. That means that therefore Pythagoras' theorem applies, so it must be a right angled triangle. And indeed, because it's a right angled triangle, the hypotenuse then would be the largest side, which is AB, okay? With AB, the hypotenuse. Oh, is that it? Hypotenuse, there we are. Okay, well, if AB is the hypotenuse, the largest side, well, actually, the hypotenuse would be the diameter, because if the right angle's there, the hypotenuse is opposite. The hypotenuse is opposite the right angle, so it faces the right angle in that way. So therefore, the diameter would then also be the hypotenuse, which would then be AB. So therefore, AB is the diameter. No, I should say a diameter. because you can have many diameters. Yeah, okay, so there we are then. So that hopefully that makes sense. And in general, if you are asked to prove that some triangle is indeed a right angle triangle, or need to prove some angle in a triangle 90, you should try and do Pythagoras theorem, because if Pythagoras theorem applies to all three sides, if you work out the three sides, and then you can you show that Pythagoras theorem applies, then that's showing that the triangle is a right angle triangle. Okay, so we've got that out the way with. The part B says then find the equation of the circle. Okay, how much room do we have? Okay, cool. So now we proved it is indeed a diameter. Well, we're going to use that fact then. Well, actually, as we discussed then a bit earlier, if it's a diameter, well then the midpoint is indeed going to be the centre of the circle. So then we can find the midpoint. So then midpoint of AB is going to be, well, I'm going to note that A is the coordinate. I'm going to write it down here so I don't have to keep scrolling up. A is minus 8, 1. And B is 4, 5. Okay, so the midpoint of AB then, which are these two coordinates, well then we just add the x values together, minus 8 add 4 over 2, and then add the y values, divide by 2, 1 add 5 over 2. That goes to, minus 8 add 4 is minus 4, over 2 would be minus 2, 1 add 5, 6 over 6, and 6 over 2 is 3. There we are. Okay, so therefore that's the centre. Because it's halfway on the diameter. Cool. Then, well, to find the equation of the circle, which again, remember, is in this form. Well, the centre would correspond to AB. Well, then we just need the radius. Well, how do we find the radius? And again, the radius is the distance from the edge of the circle, well, the outside of the circle, to the centre. But we know 3 points on the centre, on the outside, and we know the centre. Again, we can just find the distance between any point outside, say B, and the centre. And so that distance would be the radius, okay? So then we just need to find the distance of the centre to B, okay? So let's take B then. Distance from centre to B. And that's going to equal B is there. I'll box it actually. That's B, and this is the centre. The distance between those 2 points then is then going to be changing x, all squared. So changing x, so minus 2 for the centre, take away 4 for B, all squared, and changing y. That's 3 from the centre, then y 5 at B, take away 5, all squared. Then put that in the calculator, you get you get 2 root 10, okay? Therefore radius equals 2 root 10. So therefore radius squared, or r squared, is going to be 2 root 10 all squared, which will then get me 40, okay? Actually, that's one more work at the radius, but we actually could have been a lot quicker with that, couldn't we? We didn't need to complete that, actually, did we? Because we know that it's also, the radius is half the diameter. But actually, we did work out the length of the diameter already, the overall from A to B. But that's 4 root 10. So actually, the radius would then be a half of 4 root 10, it'd be 2 root 10. Okay, so we could have cut down on that, actually. But we didn't need to do that, but there we are. So we get 2 root 10, which is half of 4 root 10. But yeah, you can do it that way, not much longer, but there we are. Anyway, so we've got our radius then. And we've got our centre, therefore we've got the ingredients to find the equation. So the equation of circle is x then, well, if it's minus 2 here, it'd be plus 2 in this formula. And then y, where it's plus 3 at the centre, so it's minus 3 here. then r squared is 40. There we are. Cool. Okay, let's have a look at this example then. We are given 3 points again that lie on the circumference of the circle. The equation of the perpendicular bisector of PQ is y is 2 of x. Find the equation of the perpendicular bisector of PR. Okay. So I guess we could just do a rough sketch of the circle, see what it looks like. I'm not. Tell you what, I'll draw a grid as well. Okay. X, Y. Let me just draw the 3 points in. Okay, so P is 316. That'd be. Let's say that's there. 316. Q is 1112, so it's probably going to be like there somewhere. And R is minus 76, that's going to be probably there somewhere. Okay. R minus 76. So we are told that forms a there's a 3 points on the circumference of a circle. We also told the perpendicular bisector PQ. So that's P. So then the line PQ would be like that. Then the bisector would be the perpendicular bisector would be there. Okay, and that'd be y is 2 of x. Then we need to find the perpendicular bisector of PR. So if we draw that line there, and then the perpendicular bisector would look like that. We need to find that equation. Okay, so okay. Well, again, for finding a perpendicular bisector, well, it's on the line PR. We know both points P and R. So then it's going to go through the midpoint. So then we need to work that out firstly. So midpoint of PR. Then that's going to add the x coordinate. So 3 for P, add minus 7 for R over 2. Then we add y, so 16 for P and 6 for R. And then that's going to get me 3 minus 7 is minus 4, over 2 is minus 2. 16 add 6 is 22, over 2 would then be 11. Cool. Okay, so no point. So then we need the gradient, but then again, well, it's perpendicular to the line PR. So if we know the gradient of PR, we can then do the negative reciprocal, but we can work that out. The gradient M of PR is the change in y, change in x, right? So again, changing y firstly for P was 16 for P, take away 6 for R, over changing x, so then 3 for P, and then take away minus 7 for R, and there we are. But that's going to be a double negative, that will turn to a positive. 16 take away 6 is 10, 3 add 7 is 10, therefore it'd be 1. Okay, so that's the gradient of PR, therefore gradient of perpendicular bisector, that's going to be what? Well, it's a negative reciprocal, so negative, well, then negative 1, the reciprocal is just 1 again, right? So there we are. Cool. So then we can start to deduce an equation for the bisector. So y would then be mx plus c. We know m is minus 1, so it'd be minus x plus c. Okay, but then we just need to find the c, and that's where this midpoint would come in, because we can substitute that point then onto the bisector, because we know that midpoint, it passes through the bisector passes through the midpoint. So substitute minus 2, 11 into that line to get y is 11. Minus x would be minus, well, minus of minus 2, add c. Well, that goes to 11 equals plus 2, add c. Therefore, c, if I take away 2 to both sides, I get 9. Therefore, y is minus x plus 9. And there we are. That's my bisector, PR. Cool. Then for part B, as it says, and hence find the centre of the circle. Okay. Well, we know the bisector PR, and we're also given the bisector PQ. We got the two equations. We also know that all perpendicular bisectors again intersect at the circle, set the centre of the circle. So we need to consider the intersection. That will give me the centre, okay, which I want to work out. So then I'm going to say for part B, intersection of y is minus x had 9, that bisector, and the other bisector, y was 2x, was it? Yeah, there we are. So then we need to consider their intersection. That means they equal each other. So therefore, if they equal each other, I can then substitute one into the other. So 2x then would equal minus x at 9. If I add x to both sides, I get 3x is 9. So then x is 3 if I divide by 3. So then that's x then. So then therefore I need to find the y coordinate, the y part to get the y coordinate. So if I know x is 3, I can substitute that into either equation there or there. Well, let's just substitute it into y is 2x. So if y is 2x, then y would be 2 lots of 3. That would be 6. Therefore, the centre, there, which is when the two bisectors intersect, would be the point 3, 6. There we are. Cool. And then part C says, then work out the equation of the circle. Well, we already have the ingredient, the centre ingredient to it. So if we know the centre is this, then the equation would look like x take away 3, and then y, well, not plus it, be minus 6 instead, be r squared. Okay, well then we just need to find the radius. We know that these 3 points are indeed on the outside, the circumference of the circle. We just worked out the centre. Well, then the distance between the centre and any point outside would give me the radius. That's what I'm going to do then. I'm going to take r here then, minus 7, 6, right? So I'll do that here. R is minus 7, 6. And we know the centre is 3, 6. So distance from centre to R, which will then give me the distance from the centre to the circumference of the circle, which would be the radius. That would then be the root of change in x. So minus 7 take away 3 all squared. Then change in y would then be 6 from R, take away 6 from the centre, and that would leave me with root then minus 7 take away 3 all squared, add 6 take away 6 all squared. That would give me 10. Okay, therefore the radius is 10, but then we need r squared, don't we? So r squared would be 10 squared, which would be 100. But then we got our equation then. Then we can substitute that in to get x minus 3 squared, add y minus 6 squared is indeed 100. And there we are. So that's sort of like the recipe, right? Given 3 points on an outside of a circle, or any 3 points, we can then find 2 perpendicular bisectors. Well, in this case, we were given 1 already. We then found another 1. Then we intersected them because we know they all must pass through the centre. That allows us to find the centre, and therefore we can find the radius by considering a distance from the centre to the point outside. Then we got the equation. There we are. So that's how we can find a circle given 3 points. And there we are. Okay, and we're going to practice this even more in this question here. So then we're given these points again, R, S and T, which lie on the circumference of a circle C. Find the equation for the circle. Okay. Okay. So again, I can perhaps consider a sketch here of a general circle. I'm not too worried about the accuracy again. I'm just going to plot the points. Okay, well, R's minus 2. So that's probably going to be the furthest to the left, say there. Then S is 4, so that'd be the next along, say there. And T is 10, say like there, okay? I'm just roughly labelling where the points are, considering to the x coordinates, right? So how left to the or right to the circle they are. Anyway, I'm not too worried about the accuracy, so there we are. And I'll label the coordinates too. -2, 1. S is 4, 3. And T is 10, -5. Okay, so we visually see what's kind of going on. And there's a circle between them, right? I can make a circle. But I need to find the equation of it, right? So just given any 3 points, I need to find the circle that defines it. Okay, so we kind of started from scratch really, but the rest of the methods are the same by considering the perpendicular bisectors. But that's what we're going to do then. So let's consider the points joining these lines. Then we need to find 2 perpendicular bisectors. Let's firstly consider RS, right? The line RS. And then consider the perpendicular bisector to it, right? And that'd be perpendicular. Okay, so firstly, any perpendicular bisector is going to be going through the midpoint. So we need the midpoint of RS. So that's going to be then adding the x coordinates together for R and S. That's -2, add 4 over 2, and then add the y coordinates. So we have 1, add 3 over 2. And then that get me -2 add 4 be 2 over 2. Well, 2, and then 2 over 2 be 1. The 1 add 3 is 4. 4 over 2 is indeed 2. Cool. Then we got the midpoint, so we know a point that goes through the bisector. Okay, but then we also know it's perpendicular, so we need to consider gradients. But we can also find the gradient m of RS, the gradient between R and S. That's going to be changing y, changing x. So let's consider S first. So y is 3 at S. Take away the y at R, which is 1. Then we do changing x. So 4 now is at S. Take away -2 for R, and then so that would give me, well, that'd be a positive, double negative. So then that's 3 minus 1 is 2, and 4 add 2 be 6, and that will go down to a third. Okay, but then therefore the gradient of the bisector would be perpendicular. So negative reciprocal, right? So it's going to be around negative, and then the reciprocal 1 over 3, we flip the fraction to be 3 over 1, which is just 3. So -3. So therefore we can say that the equation is y is mx plus c for any line, but we know m is -3 here, the gradient plus c. So then we need to find that c, where we can substitute this midpoint in, because that passes through the bisector too, to find that missing number. So sub 1, 2 in. We then get y is then, y be 2, and then -3 of x, which should be 1 plus c. That's 2 is -3 add c, but then c, if we add 3 to both sides, will be 5. Okay. Therefore, y is -3x plus 5. Cool. So that's one bisector, but I need something else to equate it to find the intersection, to find the centre. Let's then consider ST, the bisector ST. Okay, there we are. So again, that's going to be perpendicular. So then we're going to just do the same thing. So then we're going to do S to T. And so then first we need to do the midpoint between S and T. So midpoint of ST is going to be, well, S and add the x values together, so 4 and 10 over 2, and then add the y part, so we have 3 and -5 over 2. That would get me, 4 and 10 is 14, divided by 2 is 7, then 3 minus 5 is -2, divided by 2 is -1. There we are, cool. Then again, the bisector be perpendicular, so consider gradients. The gradient of the line ST is again changing y, changing x. So at t it's -5 for y, take away 3 at s for y, then changing x, so then it'd be 10 for t, take away 4 for s, and that would get me -5 minus 3 is -8, over 10 minus 4 is 6, So that'd be minus 4/3, I believe. That simplifies too. Yes. There we are. So that's my gradient. But therefore the perpendicular bisector to this, which is perpendicular, hence the name, well, it's going to be the negative reciprocal, right? So negative of negative 4/3, right, it's going to be positive then. And so then the reciprocal 4/3 will then go to 3/4 by flipping the fraction. There we are. So then we can start to deduce an equation for it. So y is mx plus 3 will go to 3/4 x plus, well, not plus c, because I'm not using the same c here. Let's say plus d, using a different letter. Okay, but then I need to find that d, that other unknown. Well, I know a point on the line to substitute into, which is 7 minus 1, the midpoint. So I'm going to sub minus 7, 1 into here, to then get, oh no, 7 minus 1, sorry, the other way around. Yes, okay. If I do that, well, y is minus 1, and 3/4 of x is 7, plus d. Therefore, d, well then, well, 3/4 or 3/4 of 7 is 21/4. Then I take away 21/4 to both sides, so minus 1 minus 21/4 gets me minus 25/4. There we are. Therefore, my equation then for that bisector is 3/4 x minus 25/4. There we are. So now we found two bisectors. We should equate them together, because as we can see there, they will eventually intersect, and they intersect at the centre. There, at C. The centre. Okay, cool. So, if we then, how should we write this? Y is minus 3x plus 5, and y is 3/4 x minus 25/4. That's when we equate them together, so the both equations are together. Then if we substitute one into the other, well, 3/4 x plus minus 25/4 gets me minus 3x plus 5, okay? If I just equate the two lines together, because they're intersecting, okay? Okay. Oh. Okay, but then we've just solved for x. So first I'm going to add 3x to both sides. So 3/4 x add 3x gets me 15/4x. And then I'm going to add 25/4 to both sides, and then 5 add 25/4 gets me 45/4. Then if I then divide 15/4 to both sides to just get x, I then get x is 45/4 divided by 15/4 to get me 3, and there we are. So that's my x part, and then I need the y part to get the y coordinate. So then therefore y, I can substitute x into either equation, here or here. I'm going to substitute it into minus 3x plus 5. So then y would be minus 3x, so minus 3 of 3, add 5, which will then get me minus 9 add 5, that'd be minus 4, I believe. Cool. Therefore, my centre, which is then the point of intersection, remember, of the two perpendicular bisectors, because if two perpendicular bisectors intersect, that means that point must indeed be the centre, because the centre must be on every bisector again. Therefore, the centre, which is the intersection, well, x would be 3, y is minus 4. Cool. Okay, so again, it's asking us to find the equation of the circle, so we can start to fill that in now because we found the centre. So therefore, x, and then take away 3 squared, and then add y, and instead of take away 4, and then add 4 here, and that's going to equal radius squared. Well, we don't know the radius, but that's the last thing we need to work out, and we can find that. Again, how? Because again, now that we know our centre here, which I believe was 3 minus 4, was it? I think. Well, we've got the centre, so the distance from the centre to any of these 3 points on the outside of the circle, say from R to C there, that's going to give me my radius, right? So I can just find the distance between, let's say R of minus 2, 1. And centre, which was 3 minus 4. So therefore the distance between them is then the root of the change in x squared, so for the centre it's 3, take away minus 2 for r, all squared, then for minus 4 for y at the centre, take away 1, all squared, so we do the change in y squared, and putting all that in the calculator then gets me, well, 3 take is, then that'd be 3 plus 2, because I have a double negative there, that will turn to a positive, 3 add 2, all squared, then add minus 4, minus 1 all squared, to then get 5 root 2, okay? And that's going to be my radius, which will then be r, which is 5 root 2. But, again, for this equation, I need r squared. So, therefore, r squared is that squared, right? 5 root 2 all squared, which should be, if we put that in the calculator, 50. There we are. Well, there we are then. So therefore the final full equation of the circle will be x minus 3 squared plus y plus 4 squared equals 50. Okay, so we filled in, substitute r squared into there. There we are. Cool. So yeah then, so that's really the sort of recipe for given 3 points, you can find the equation of the circle that makes those 3 points. Cool. So yeah, really the main sort of idea is to consider the bisectors, right? Once you've found 2 bisectors, perpendicular bisectors I should say, then you can find their intersection, which is the centre, and therefore the radius as well. Okay, cool. Okay, let's have a look at this one. We are given now here points D, E and F, and we're given actually that D, E, F is 90 and B is greater than 0. For part A, we need to show that B equals 1. Okay, so we just got one missing y coordinate there. Okay, well, in that case, well, actually, again, it's perpendicular. So actually, notice that line and this line are perpendicular. So can't we just consider the gradients? Really? We're only missing one y coordinate, so we should be able to do that. Anyway, we can consider the perpendicular lines, right? So that'd be the lines ED and EF, and they're perpendicular, right? Because they're at right angles to each other. Well, then we can find the gradient. So therefore, M of ED, the gradient between the points E and D. Well, I know it's going to have B in there, but again, B is just a number. So let's just work out the gradient anyway, right? So with that in mind, then, so let's do D first. So y at D is minus 3. Take away B, which is the y at E. Then do change in x. So then minus 12 for D. Take away minus 10. And actually, we can simplify that to a little bit to minus 3 minus B over, well, minus 12 add 10, that'd be minus 2. Okay. And there we are. Then we can find the gradient of EF. And so let's take F then, to be first. So changing y then, firstly, well, minus 5 for f, then take away b again for e, and then we do changing x, so 2 at f, take away minus 10 again for e, and that's a double negative, so there we are. So then that goes to minus 5 minus b over, well, 2 add 10 would then be 12, there we are. Okay. Right, so then they are perpendicular. Obviously it looks a bit nasty because there's like a B as a letter in both. But we can still do the perpendicular, we can still do the negative reciprocal, right? The perpendicular, so that means the negative reciprocals of another. So, well then that's what we're going to do. So therefore, because they're perpendicular, okay, so then the gradient here then of ED, so minus 3 minus b over minus 2, then that's going to be perpendicular, right? So the negative reciprocal of this. Now it looks a bit weird because we've got a b in there, so it's a bit, how do we do that? But let's just take it literally, step by step, right? So the negative reciprocal, so literally negative of the reciprocal of this. So we reciprocal then just flips the fraction. So instead it'd be 12 over minus 5 minus b. Okay. Then I guess we can then times by the negative. So minus 3 minus b over minus 2 would equal minus 12 over minus 5 minus b. Now, we could jump to equation, but there's a lot of negatives here, so we can actually simplify it, make it easier for ourselves. By then just divided by a negative, right? So if I divide this left fraction by minus 1, so I could say it's minus 3 add b over minus 2. Well, that would cancel then, to then just 3 add b over positive 2. And then I could do the same here. Well, this fraction here is the same as minus 12 over minus 5 plus b. I can factor the negative out. Then I can divide by the negative, right? To then get 12 add b add 5. Well, 12 over b add 5, sorry. So that's a lot nicer that we're there. So that'll make the equation a lot easier to deal with. Now, I talk about equation. Well, then, to get an equation to solve, it's just cross-multiplying because we have an algebraic fraction, right? Which you would have been familiar with Jesus. See how to solve equations like this with fractions. So then, we do b add 3, b add 5, then equals 12 lots of 2. Cool. Then we just expand the bracket, so b times b is b squared, b times 5 is 5b, times 3b will then be 8b, and then 3 times 5 is plus 15, and that's going to equal 12 times 2 is 24. Okay, well then I then need to take the 24 away to both sides, so 15, sorry, take away 24, gets me minus 9, and that's equal to 0. Okay, well then I could solve the quadratic. To get b, then is by using the formula because I'm lazy. To then minus 8 plus or minus the square root of b squared is 8 squared. Take away 4 lots of a, well 1. C, which is minus 9. Over 2a, which is 2 lots of 1. I put that in the calculator, and hopefully 1 should be one of the solutions because they told me b needs to be 1. So, yes, I do get 1 there, so we're on the right tracks. So b is 1, or the other value is minus 9. Okay, so we've got 2 values then. So let's check with the question then, because then there might be another condition which we need to consider. And here we are. We're told b has to be greater than 0. That allows me to then rule out minus 9 to only get 1. There we are. There we are then, cool. So then, oh, let's go back. Therefore, b is greater than 0, therefore b is 1. There we are, that's part A done. Okay, and the weird part, the mark, if you ever do check the solution about the mark scheme to this question, they do it a lot more complicated, I feel like. They could literally consider Pythagoras theorem and do all 3 distances, which is quite crazy when you got a B, when you got some algebra in there, and expanding all those brackets and so on. Considering the gradient is the far better and quicker method in this case to what the mark scheme does there. Okay, so then part C says find the equation for C. Okay, well, okay, so that's going back to then the fact that we have an angle in a semicircle. So because that's a right angle, then that means for that to happen, because of the theorem looked at earlier, that must be the diameter, because it must be a semicircle. So that line must be a diameter to split it into two semicircles. There we are then. So that must be the diameter. So I don't have much room for here actually, unfortunately. I'll try and squeeze it maybe here somewhere. So DF is a diameter then, right? Due to the circle theorem, as angle in a semicircle is indeed 90 degrees here, which is right angle. Okay, cool. Well then, what do we know about the diameter? Well, the midpoint again must be the centre of the circle, so we can find the midpoint between D and F. So midpoint of D and F is then going to be, well, if we add the x coordinates, well, minus 12 for D, and then 2 for F over 2, and then for Y, add the Y coordinates, so minus 3 for D, and minus 5 for F over 2. That will then get me, well, minus 12 over 2 is minus 10 over 2, which would be minus 5. And then minus 3 minus 5 minus 8. Divide that by 2, I get minus 4. But therefore, that's my centre then, because it's the midpoint of the diameter. Okay, so we've got this centre. So start again to fill in my equation. So it's x. Well then, instead of take away 5, it's add 5 here. And then for y, instead of take away 4, I add 4, all squared. That's going to equal r squared. So then I just need my radius. Okay, well, there are multiple ways I could find the radius, but let's make life easy. I could perhaps find the... actually, yes, that's what I'm going to do. Never mind. I can find the distance between C, the centre which I found out, and any point. Let's take F then, right? That'll give me my radius. I was going to say perhaps you could find the length of the diameter. But we don't have the length of the diameter, so we're just doing more work for ourselves in that case. So let's just find the distance between the centre and F, was it? So distance between the centre, which is minus 5, minus 4, and if I get rid of all this, and the angle, the point F, which is 2 minus 5. That would then be the distance of the root of the change in x squared, so minus 5 take away 2 all squared, then the change in y squared. Well, minus 4 take away minus 5 all squared. Put that in a calculator. I am sorry to squeeze this in. I don't have any room to unless I go over the next question. And that's a minus 2. Let me write that bit neatly. Minus 5, there we are. So I put that in the calculator. That would give me my distance between the centre and the point outside on the circle, which was R, I think, and the F. Minus 5 take away 2 all squared. Add minus 4, and then that'd be positive there, right? Double negative. Minus 4 add 5 all squared. That gets me 5 root 2. Therefore, the radius is 5 root 2, which is again is that distance. So r squared is root 5. 5 root 2 all squared, sorry. And that will be 50. There we are. Well, there we are then. So if I get rid of that then. So b is greater than 0. Okay. So then I could start to then I got my full equation of the circle. So therefore x, if we take that, oh, that's a bit messy. If I take that equation I've done there, so x plus 5 squared, add y plus 4 squared, I believe, was it? Yep, and then that's r squared, but r squared, as we saw, was 50. There we are. That's my equation of the circle. Cool. Okay. Um. Okay, so I have this question then. So we're told the circle has equation x squared. Let me get rid of the box now, it's a bit distracting. The circle has equation x squared and 2x y squared minus 24, y minus 24 is 0. First of all, find the centre and radius of the circles. That's quite bog standard, really. So we need to firstly complete the square to get it in the normal form of the brackets that we're used to. So then we complete the square on the x part. So x are here. So x and then a half of 2x plus 1. All squared, take away 1. And then add, well, y. And then a half of minus 24 is minus 12. All squared, take away 12 squared, would be minus 144. Then we have the minus 24 at the end there, equal to 0. Cool. Okay, well then let's bring the brackets together. X plus 1 squared, add y minus 12 squared. And then minus 1. Minus 144 minus 24 gets you minus 169 equals 0, but then we can move that to the other side to make it equal to positive 169. There we are then. So therefore we can deduce at the centre in this case, well, it'd be minus 1 instead of plus 1, and instead of minus 12 it'd be plus 12. And the radius, well, radius squared is 169, so the radius would be root that, and that is actually 13. Cool, there we are. Should be fairly straightforward at this point. There we are. Then part B says, the points A and B both lie on the circumference of the circle. Show that AB is the diameter. Okay, so if we then have to say the point A, then the point B, and A is minus 13, 17. B is 11, 7. Well, if AB is the diameter, then the midpoint must then be the centre. Okay, so we need to show that we can find the midpoint, and the midpoint should indeed give us minus 112. So therefore the midpoint of AB, that's going to be, well, if we add the x parts of A and B, minus 13, add 11, all over 2. Then for y, we add the y coordinates, we have 17, add 7, all over 2. That will get me, minus 13 add 11 is minus 2. Minus 2 divided by 2 is minus 1. 17 add 7 is 24. 24 divided by 2 is 14. No, 7, no, sorry, 12. 24 divided by 2 is 12. Oh, hang on a minute. It is indeed the centre. So therefore, midpoint is the centre of the circle. Therefore, AB must be a diameter. There we are. Nice. Cool. Then part C then says that the point C lies on the negative x-axis and angle ACB is 90. Find the coordinates of C. So I think at that point it's probably best to probably plot the coordinates, I think. So if we have an axis there. Okay, so that's point A. So A is minus 13, 17. So A is probably going to be up there somewhere. There we are. B is 11, 7. So that's probably going to be there somewhere. And C, okay, well we're told C is on the negative x-axis. So the x-axis, obviously, the x-axis, right, the line there. Well, it's negative, so it's going to be somewhere on that line, on that part of the line there. I guess we can just maybe say C's there, perhaps. I don't know. Then if we connect the lines together, There we are. And actually, yeah, it does look like a right angle triangle, but we do need to, and we are told it is 90, so yes, it is indeed that. We need to find the point C. Okay. Well, again, C, if it's on the x-axis, we already know that it's x has an x value, right? An x coordinate. We don't know what that is. We call it x. Well, y would be 0 because it's on the x-axis. Well, then it's the same sort of problem that we looked at earlier, where it's kind of where it's perpendicular, right? The line AC is perpendicular to BC. We can then find that x by considering the gradients, can't we? AC is perpendicular to BC. Therefore, well, then we consider the gradients then. They're perpendicular, so the gradient of AC firstly. Well, A is here. I've written that here. So the change in y, change in x. At C, well, y is 0. Take away y at A, which would be take away 17. Then we do change in x, so it's x for C. Obviously, we want to find x, so it's just x there. Then take away minus 13 for x at A. Then that will go to 0 take away minus 17 minus 7. Take away 17 minus 17, sorry. Then x, and then that'd be a double negative, which would be a positive. So then that'll go to x plus 13, and there we are. I can't do anything more with that. Then we can also consider the gradient of BC. And again, B is there. So then if you do change in y between B and C, well, y, again, C is 0. Take away the y at B, which would be 7. Then change in x, so x at C. Take away 11 at B, and so that will go to 0 minus 7, which would be minus 7, over x minus 11. And there we are. Cool. Now, again, they're perpendicular. Okay, so the two gradients will be negative reciprocals. So the gradient AC here, minus 17, over x plus 13, that's going to equal, well, they're going to be negative reciprocals of each other. So that will be equal to the negative of the reciprocal of this. So you just flip the fraction, because that's how reciprocals are. That's what reciprocals do, sorry. You flip the fraction, so it'll be x minus 11 over minus 7. Okay. Okay, well then, actually, then, let's go down. Well, I can then simplify what I'm doing. I can then divide by -1. I can get rid of the negative to both fractions. Because there's a negative outside here, I can just say that's a negative outside the left fraction. And I have a negative on the other fraction, the right one. Divide by the negative to then get 17 over x plus 13. Is just equal to x minus 11 over minus 7. I only did that to simplify things for me. Because then I can then get an equation from this by then again considering I forgot what you call it now. Cross multiplying. It left me there. You cross multiply both fractions to get to then get 17 lots of minus 7 is x plus 13, x minus 11, and there we are. Okay, well then at that point, we then can expand the bracket. So we have 17 times minus 7, which is minus 119, is equal to x squared, and then x times minus 11, and then x times 13, minus 11x add 13x, that'd be plus 2x. And then 13 times minus 11 is minus 143. Then to get a quadratic equation, I need to move this number to the other side to then get x squared plus 2x, and then minus 143 add 119 to both sides to get to minus 24 equals 0. Cool, so that's a quadratic equation then. I can then solve that. So x, and if I use the formula, again because I'm lazy, that'd be minus 2 plus or minus the square root of 2 squared. Take away 4 lots of a, which is 1c of minus 24 over 2a, which is 2 lots of 1. So if I do that, put that in the calculator, I get x is 4, or -6. Cool. So I've got two values there, but obviously I only want one value. So again, we need to look at the question to see which one to discard, to get rid of. And actually, it says it's on the negative x-axis, remember? There. So it needs to be negative x value. So that means, if you go back down here, we need to take -6. So that means x is negative. So x is -6. But therefore then, the coordinate c, which again is that point -6 for x, the coordinate then is going to be -6 for x and 0 for y, because it's on the x-axis, remember? As we discussed, which means it will be y0. And there we are, cool. So that is the coordinates for c. And let's move on. Question then. And we're given 4 points this time, quite interesting. That line of circle. Show that ABCD is a square. Okay, so we've got another sort of shape geometric question, which we did a bit when we looked at some examples like that before. So to prove it's a square then, and then a square, obviously think about it, all sides are equal. So a square has all equal sides. But also all the angles are 90 degrees as well. And all angles inside are 90 degrees. And that's what we effectively need to show then. Okay, so then if I draw a plot of points then to visualise what's going on, that will help me. Well, A is -1,9, so it's going to be probably up here somewhere. And D is 610, so that's going to be up there somewhere. B, sorry, not D. B 610. Then C 73, so that's probably going to be down there somewhere. And D 02, so that would be there. Okay. So then if we connect the points then, hopefully should resemble square, and we can see what we're working with. There we are. Okay, I mean, it looks more like a rectangle, but I don't know. Just maybe our diagram's a bit weird. Okay, well, if it's a square then, well, first, probably the easiest one to prove that all the sides are equal. Well, how are we going to find the sides? Well, we know the points, so we just find the distances. So there we are. So we're going to need to find all 4 lengths. So firstly, let's get cracking then. So that firstly then I know it's the side AD. So AD, the distance of that between D and A. Well then that's changing x squared. So D is 0 for x, take away -1 from A. And then changing y would be 2, take away 9. All squared. That would get me, put that in the calculator. 0, add 1, all squared. 2 take away 9 all squared, it gets me 5√2. And so hopefully all the rest of them should come out 5√2 as well. So that's AD. Then let's do the this line, AB, that side. Oh. So AB is then the change in y, change in x of B and A, all squared. So then B, the change in y is 10 there. Then take away the y at A would be 9. I'm going to write my points here actually, so I don't have to keep going back. A is -1,9. B is 610. C is 7.3. And D is 0.2. Okay. Okay. So then AB, the change in x is 10 take away. Oh, hang on. Oh no, I did change in Y. Okay, so no, let's do change in X first. Okay, I don't know why I did that. So changing X between B and A is 6 take away minus 1 all squared. Then the change in Y will be 10 take away 9 all squared. That would get me, put that in a calculator. And I should know I got it right because it should come out to 5 root 2. So the 6 add 1 all squared, double negative. Then add 10 take away 9 all squared gets me 5 root 2. Cool. Then I need to find another side. Let's take BC. That side now, I haven't done that one. So then the side BC, the length of that is then between B and C. The change in X is for C it's 7, take away 6 at B, all squared. Then the change in Y is 3 take away 10, all squared. That will get me 5 root 2 again. Cool. So I'm on the right track. And then lastly, the other side, the last side, is DC or CD there. Okay. So then the side CD, the distance between that, well, the change in X then for D 0 take away 7 at C all squared. And then change in Y would be 2 take away 3 all squared. That would get me 5 root 2. Cool. There we are then. So therefore AB equal AD, that was the first one here. AD equals AB equals BC equals CD. Now that tells me those four sides are all equal. So all four sides are equal. And they obviously all equal 5 root 2. Okay, so that's the first bit. Then I need to show that the angle inside is 90. Okay. Well, then I can show that they're perpendicular because I can find the equations of the lines. So let's take the line AB here and the line AD, okay, and hopefully the angle between them should be 90 there. Okay, well, how are we going to do that? We're going to find the gradients then. So MAB, firstly, the gradient between A and B is changing Y, changing X. So 10 at B, take away 9 at A. Then changing X would be 6 at B, take away minus 1, which would then be 10 take away 9 is 1. And then that's a double negative, so 6 add 1 would be 7. So it's a 7th, okay? And the gradient of then AD, which is that one then that's changing Y, changing X. So at D, Y is 2, take away 9 at A. Then we do 0 at D, take away minus 1 at A, and again that'd be a double negative. So that'd be 2 take away 9 is minus 7, and 0 add 1 would be just 1. So that will go to, and I should probably get rid of these points now, I don't need them, taking up room. Well, that just simplifies to minus 7th, right? Minus 7, sorry. But there we are then. So therefore, we can conclude they're perpendicular because they're negative reciprocals. We can show that because remember, if we multiply them together, that will indeed get me minus 1, which then tells me they're perpendicular. So AB and AD are perpendicular. So the angle so the angle here then, which would be angle BAD, we would say. And remember, you can name an angle because you go in alphabetical order from B to D, but A is in the middle because the angle is at A. Okay, so that's how we label angles. So that's going to be 90 then. Okay, so then that's 90. Well, then that also means that that because all the sides are equal, that means, although this diagram's a bit weird though, it doesn't look like they're equal, does it? It looks like some sort of parallelogram. Well, actually a square is a parallelogram. Anyway, it is a square. I don't know why the diagram looks like that. Probably bad scaling with my axis. Probably that's why. But if all the sides are equal, that means the angles between all the lines have to be the same. Okay. Because say if we had 90, you can kind of visualize it a little bit. Because say that's 90, and these that's A, B, and D, right? We've shown that all the sides are equal. Well, if say D, oh no, that's D. Sorry. Say if we had therefore the same side there at C, if you wanted to make an angle here that was at 90 at B and between B and C and A, say you want to make it acute, it would have to look like that instead, right? To make it not 90. However, then the sides would then not be the same. So because of the fact all the sides are the same, we can kind of then take for granted in a way that the fact that if this is 90, then all the angles must also be 90. Okay. So therefore we can then quickly jump to the fact that all the angles are 90. So all angles inside are 90 as well. But therefore then, because both criteria are met, that all the sides are equal and all the angles are 90 because they're perpendicular, that means therefore that the ABCD must be a square. Okay. And there we are. And that's really all the justification they are looking for there. Okay, cool. Okay, so that's probably the hard part done. But it's a good idea. I do pick questions like that intentionally, even if it's not entirely relevant to this section, because they do tend to ask time to time to just prove something is a parallelogram, or something it's a rectangle, something it's a square, and you do need to know how to kind of do that, to do kind of embed questions like that here and there. But this is a nice question. Anyway, then it says for part B, find the area of ABCD. Well, I'm going to use this square diagram I have up here. I've drawn. So that's all 90. And we know if this is A, B, C, D. Again, we know all the sides are 5 root 2, 5 root 2. Oh, we worked that out in part A, right? But therefore for part B then, simply the area, and we know of a square, it's just the side times by itself. So it's going to be 5 root 2 times 5 root 2. So then that would be, put that in the calculator. You get 50. There we are. And that'd be 50 units squared. Okay, very nice question part there. Then part C says find the centre of the circle. Okay, so a circle, so these all 4 points lie on the circle. Okay. Well, well, it's interesting because we have a 90-degree angle there, right? Well, then, say if we create a right angle triangle between a diagonal, and say if all these are on a circle, say if it looks a bit like that, although it looks a bit rubbish, right? That's sort of what's going on, right? The square is inside the circle, and we have a 90-degree angle. If we create a diagonal there, that will create 2 semicircle triangles, right? Well then therefore the diagonal must be the diameter, right? Well, it makes sense, no, sorry. So it must be the diameter though, right? Because we have an angle in a semicircle. Because of the fact that it's a square, the angle's 90. So let's consider the diameter BD then, right? So I'm going to say for part D, we have an angle in a semicircle. Therefore, what was the diagonal? Diagonal BD. line there must be a diameter. I'll say diagonal BD. Okay, cool. Well then, what's it asking for? The centre. Well, okay, that's easy. Well, if it's a diagonal then, well, not a diameter. Well, it is a diagonal, but a diameter. Well, then the midpoint's going to be the centre, right? So if I then redraw that line BD down here, B there to D there, and I let me label the points again. So B was 610, and D was 02, was it? There we are. Therefore, the midpoint of that's going to be the centre. So we just need to consider the midpoint of BD. Right, again, that's going to be adding the x and the y parts divided by 2. So add the x parts first. That'd be 6, add 0 over 2. Then if we add the y parts, we get 10, add 2 over 2. And then that will go to, well, 6 over 2 would be 3. 10 plus 2 is 12. 12 over 2 is 6. Therefore, my centre is then indeed 3, 6. And there we are. Cool. Not kind of nice little last question there, but yeah. So yeah, that's circles. So yeah, so as I said at the very start, you do need to use the theorems like we did in the questions there. You don't have to prove them, but you just need to know them. Which again, as a recap, would be firstly, again, perpendicular bisector. So if we have a chord, the perpendicular bisector must pass through the centre. Okay, so if a chord there, and that's been the perpendicular bisector, must pass through the centre. The other one, which we looked at today, was if we have a diameter, that creates two semicircles. If two ends then go on to meet and make another angle there, that will then be 90. And we call that the angle in the semicircle is 90. And the last one we will be using, we used today, sorry. No, we used the other last time. Is when we have a tangent at a point, say there, then if we have the centre, then the radius to that point will then be perpendicular, okay? So tangent perpendicular to radius. We have angle in a semicircle is 90, and at any perpendicular bisector of a chord and again, remember, a chord is literally basically just a line in the circle. It goes through the centre of a circle. And see, yeah, you need to be, goes through the circle. Well, yeah, but it also goes through the centre of the circle. So you need to be able to be very comfortable with using those three circle theorems in particular. And we've seen many examples now in this section if you want to revisit them. But that is circles. That's all you need to know for circles for the exam. And also don't forget you need to you then need to consider the intersections of a line and the circle. So if you then say if a line passes through a circle twice, you'll then have to substitute that in and use a discriminant to be positive. Or if you have a tangent, like in this case here, if that tangent intersects the circle and you have the equation for both, you can then equate them, and every tangent intersects a circle exactly once, right? Oh, I can't spell. Intersects a circle exactly once. That allows you to then eventually use the discriminant to equal 0, okay? And we looked at examples like that earlier as well. So yes, that's circles, and I will see you next time.